Is that working?
That's working.
Okay, Pamela, Hubble constant, go. No,
Don't we need to like start the broadcast or
yeah, yeah,
something?
yeah. We'll get this set up. All right. Hi, everybody. My name is Fraser Kane. I'm the publisher of Universe Today, and we are going to be recording a catch-up episode of Astronomy Cast today. So we've actually got three we're doing this week. So today we're going to be recording the Hubble constant, which is going to happen right now, and then after that we're going to be doing the Cosmological Constant, aka lambda, and then tomorrow we're going to be recording explosions in space, which was a suggestion from a listener, which I think is a really cool idea for a show. So we're going to be doing that, sort of some math, complicated astronomy stuff, and then some kind of silly escapist stuff. It'll be a good week. Astronomy Cast, episode 279 for Monday, November 5th, 2012, the Hubble constant. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. Global warming is treating us really well here on the West Coast today. It's beautiful. I was wearing like shorts and t-shirt in the middle of November. We're recording this episode a little late, so it's like almost December, and still the weather is beautiful. So yeah,
we have the exact same thing here. I was riding my horse outside in short sleeves yesterday, and me and the horse were both sweaty, and that doesn't normally happen outside. We're destroying the environment in ways that allow t-shirts in November.
Yeah, thanks, global warming. As always, we are recording this episode of Astronomy Cast as a live Google Plus Hangout, and if you want to watch us record live, trust me, it's so much better. Then what you do is you circle Astronomy Cast on Google Plus, and then you'll get a event notification in your stream, in your calendar of when we're going to record our next episode, and then you can just watch us live and ask your questions, and we stick around and interact with the fans, and it's super fun. So it's a really great way. If you really enjoy Astronomy Cast, this is a great way to kind of take it to the next level. So, all right, let's rock. So when Edwin Hubble observed that distant galaxies are speeding away from us in all directions, he discovered the reality that we live in an expanding universe. Hubble worked to calculate exactly how fast this expansion is happening, creating the Hubble constant, which astronomers continue to refine and reference in their research today. So Pamela, I guess the first step is to go back. Now, we've talked about Hubble, and we've talked about the Big Bang, but I think it would be great to go back for a second and sort of talk about that discovery that Hubble made as part of his research. So what was he looking for?
Well, so the interesting thing is I need to take you back a step, actually, because it wasn't just his discovery. It all started with a guy with an awesome name who's been forgotten largely by history, whose name is Vestus Slifer. He was working at Lowell Observatory in Arizona, and he was a spectrometrist. He took images of galaxies that were not the type of pretty spiral or elliptical images that you see on astrophotography websites, but rather he took the light, put it through a thin slit and I believe a prism, and spread that light out into a rainbow that he imaged, called a spectrum, and we've talked about those in other episodes. And when he looked at these spectrums, he was able to use Doppler shifting to measure the velocity of the galaxies. And the expectation was that the galaxies would have a random distribution of motions, that some would be moving towards us, some would be moving away from us. And what he found was the majority of the nearby galaxies, while there's a couple moving towards us, like Andromeda, the majority are actually moving away, and this just completely blew his mind. And this was back in a time when we didn't actually know galaxies were galaxies. They were still called spiral nebula, and this was like all kinds of confusing.
I've mentioned this, that I've got an old astronomy book that's like from the 1920s, and if you look through it, it has the Andromeda Nebula, and it has these other nebula, and it's just so cool to see in fairly recent history that this was still their idea. Now one thing you mentioned about the sort of Doppler shifting, the red shifting, blue shifting. So what exactly was going on there with the light from these galaxies?
So when an object is moving away from you, its light will get shifted towards the red. If it's sound, the sound will get shifted to longer deeper wavelength noises, so it'll go from sounding like a trumpet to sounding like a tuba, basically. We're used to experiencing this with fire trucks. We hear them, the pitch gets more high-pitched as it's coming towards us. As it moves away, we hear this low-pitched noise. Well, light does the exact same thing, more or less. And so when we see galaxies moving away from us, light from specific spectral lines that we know the exact color they should be, it gets shifted. So if we were to use, like we use Gary Ganella's H-alpha filter every virtual star party on Sunday nights, and we see these beautiful nebulae. Well, these beautiful nebulae that show up so nicely through his H-alpha filter that only allows the light from that one transition from hydrogen to pass through. Well, if those nebulae were moving away from us at great velocities, their light would be a completely different color, and they disappear from the images.
And so is that one of the filters that astronomers use, is to look at this at that wavelength? Or
well, so what we actually do with galaxies is we don't constrain ourselves to just one wavelength generally. First of all, galaxies are kind of faint. Doing that, you're not going to get very much light in. So what we do, and we also don't know what velocity they're at. So if you don't know what velocity they're at, using a narrowband filter isn't useful. So we take all the light and spread all the light out, and we'll look at as much of the wavelength as our individual instrument allows. Some of the best instruments out there allow you to get all the way from infrared to low ultraviolet, spread out in this continual spectrum where you can see dips created from magnesium. You can see dips created from the different hydrogen lines. We see all sorts of different things as we look at these galaxies, calcium lines. And we use all these different lines to figure out the shift of the created by the velocity of the galaxies.
So Slipher, which is the best name ever, I think,
Yes.
had sort of laid the groundwork for this next discovery by Hubble, right?
Right. So the thing with what Vesta Slipher did was he couldn't actually measure the distances to the galaxy. So all he knew was a statistically improbable number of the galaxies that he looked at were shifted so that they're moving away from us. They were redshifted. Well, what Hubble was able to do was he took deep, deep images, ones that allowed him to see individual stars, that allowed him to carefully resolve faint objects in many of these galaxies. And he took a time series of them so that he was able to identify individual stars called Cepheid variables that change in brightness over time. And as they change in brightness, they do it in a very systematic way, so that one that changes over one period of time, we know it gives off one amount of light. One that changes over a very different period of time, we know it gives a different amount of light. And so he was able to use this beating of the pulsating variable stars to say, I know how much light the star actually is giving off, more or less. And that was part of the confusion. But I know more or less how much light is actually given off. I can measure how much light I see, and this allows me to calculate the distance the same way when we see a motorcycle headlight. We know roughly how bright that should be, and we can gauge the distance to the motorcycle based on how bright the headlight appears.
And so what did he discover? He was able to find these stars, these standard candles, right, in all of these galaxies around him. He's able to accurately measure the distance, which is great.
Accurately is a stretch.
He was able to a
with
order of
large
magnitude.
error bars.
Yeah, he was able to measure-ish the distance to these galaxies.
Yeah.
And what did he discover?
Well, what he found, and the problem with his accuracy, he could tell the relative distances, but he couldn't tell the actual distances. So he was able to say, this system's further away than this system. And when he made those measurements, he realized those systems that are further away are moving significantly faster than the ones that are nearby. And that is consistent with looking at an expanding universe. If you imagine yourself in a theater, and all the chairs in the theater are moving apart from one another a centimeter per movie. Well, at the end of one movie, the chair next to you is 1 centimeter away. The chair next to it is 2 additional centimeters away. And each movie, well, that one that's 2 chairs away, 2 movies later, it's going to be 4 centimeters away. 3 movies later, this just keeps increasing, and so you see that more distant chair appears to be moving faster. Well, it's not that it's moving faster, it's that the spaces between the chairs is increasing at a constant rate that makes things that are further away appear to be moving faster.
Right, right, okay. And so he makes this amazing discovery, to calculate these distances and this velocity, and sort of stumbles upon one of the most important discoveries in all of science.
And there had been people who predicted this might be the case. Einstein's theory of general relativity and special relativity, when he chewed through all the numbers, when he examined our universe in detail, one of the things that came out of relativity is the idea that when you do the calculus of space-time, there can be a constant involved that makes our universe steady state. But at the same time, if that constant doesn't have the exact right value, our universe is either expanding apart or collapsing in on itself. It's not a static place. So Einstein originally tried to use his cosmological constant to stay the universe. But there were folks like Lemaitre who said, no, our universe it could be expanding, and put these ideas forward. And so the theories were there that when Hubble put together the pieces of Vesta Slipher's spectra and his own photometry of the variable stars, when all those pieces came together, there was a complete picture in one very special moment in history.
And so, he came to this, did he actually come to this conclusion and say, okay, so we live in an expanding universe, therefore the universe had to have come from a single point in the ancient past?
Wasn't in that original paper. Now I clearly was not alive when this was happening, so I can't say what people were arguing at the conferences. I can't say what letters were getting floated back and forth, but in the literature, that original plot of distance versus velocity lays out the case for an expanding universe. Now, the two theories that emerged over time was the notion of a Big Bang, but also what's called the steady state model of the universe. This is a model that we now know isn't true, that observational data doesn't support it, but it took a while for us to realize that. And the steady state model basically says that there's new stuff coming into existence that's pushing the universe apart. So this is the idea of that movie theater that has stuff coming into it versus the stuff in the theater expanding. So you can imagine ooze pushing the chairs apart versus just what already exists,
or new chairs
apart.
New chairs pushing the chairs apart. Yeah.
Right.
So what did he, specifically, what did he calculate this expansion to be? How did he describe this? Right.
It's just a plot. That's the awesome thing, is this is a very clean, simple to look at result with a lot of error bars in the initial stuff. It was just a plot of distance versus velocity, showing as distance increases, velocity increases. Now, it was noisy, it was ugly, we only had fairly small telescopes by today's standards, we couldn't see very great distances. He ran into problems when he started observing galaxies in the Virgo cluster, because that's a gravitationally bound system. Galaxies in an individual cluster, that cluster isn't expanding, it's the separation between the clusters is expanding.
Right,
So,
we get that question a lot, right? Which is,
yeah.
Is the actual galaxies expanding? Are the solar systems expanding? Are we expanding? I know you guys have Thanksgiving shortly, so
I'm not going to answer the question, are we expanding in general?
Yeah.
In the specific case of the cosmological constant, no, it bears no effect on the human body.
It's right. It's about it's just the I guess before the concept of dark energy, it's really this kind of, you have two cars driving away from each other. and those two cars are going to be driving away from each other, and they're going to be moving apart, and they're not going to be, the cars themselves aren't going to be actually expanding as well.
But you have to be careful. It's not the objects that are moving. It's the space that's expanding.
Right. The road is growing.
The road is
with
growing.
The cars on top of it. Yeah.
And they have their emergency brakes on. They have no velocity.
They're stopped. Yeah.
Yes.
But okay, so then, but I mean, how did he actually describe this? I mean, you say it's a plot over time, but I know there's like a certain number of megaparsecs per.
Well, yeah. So
right?
back then we were still trying to figure all of that stuff out. I mean, so the poor guy in his initial measurements, we had problems. We didn't exactly know how to calibrate the distance to Cepheid variable stars. So when your meter stick is severely broken, you end up with the wrong number. So he originally ended up with the universe expanding at roughly 500 kilometers per second per megaparsec. And what that says is every million parsecs of space.
How big is how big is a million parsecs of space?
That's about 3-ish. So there's roughly 3-ish light years per parsec. So
3 million light years. So distance kind of here to Andromeda-ish. Right, because Andromeda's like 2.5 million light years away from here.
Something, yeah.
Right.
But then we're going to mix our units and add kilometers per second in there just to throw everything off.
Right.
So it's not that huge an expansion given the size of our universe. But the thing is it can be measured. Now the problem is that in order to measure it accurately, you need to be able to measure distances accurately. And that's where everything falls apart. There were none of the variable stars are close enough that we can use parallax to measure them. So we've had to use all sorts of broken ladders to build our way out to the nearby universe. And we did an entire episode on distant scales. But
so 500. If I remember, 500 kilometers per second per
megaparsec.
And so that means that if was wrong, but that was sort of his initial calculation, right?
Yeah.
So in other words, if an object is 1 megaparsec away, then it's going to be moving at 500 kilometers per second. And if it's and if it's 2 megaparsecs away, then it's moving away from us at 1,000 kilometers per second.
The space between us is expanding at
at a rate to make that other object appear as if it is moving by 1,000 kilometers per second. And if we are 3 megaparsecs, 5 megaparsecs, we are 10 megaparsecs away. Okay, great. So he did these initial calculations, and they were mind-bending, but not super accurate. But I know that astronomers have been working on this number like crazy, and in fact, we still report on it. We're still,
it's
we still write articles. Astronomers
between
refine
66 and 74.
66 and 74 kilometers per second per megaparsec. Right, which is sort of almost like a factor of 10 less than he had originally anticipated.
And what's kind of awesome about this number is for decades there was this horrible cat and dog argument between Sandage and de Vaucouleurs over whether or not it was 50 kilometers per second per megaparsec or 100 kilometers per second per megaparsec. And it was just this entire community, people picked sides and they mocked each other, and it was ugly. And I remember as an undergrad, one of my professors, he was not going to pick sides. He simply said, use 100, it's easier, move on.
Right, because it doesn't really matter because they're big numbers and chances are everybody's wrong, so it doesn't matter.
And it was only after de Vaucouleurs died that people were finally able to start settling down on the answer. And the kind of crazy thing is the answer turned out to be roughly 70, midway between 50 and 100. So both dudes were wrong. And unfortunately, like so many arguments in astronomy, the real work was only done after one of the people who made it a heated, contentious ordeal had passed away. And now we know the Hubble Key Project has done awesome work trying to refine our distance scale with Cepheids, trying to figure out the supernovae problem. And we're getting there. And what's awesome, and we've talked about this in other episodes, is there's so many different lines of evidence that we're able to look at, from using the Wilkinson Microwave Anisotropy Probe, WMAP, to look at cosmological values, to measuring the supernovae, to we still use Cepheids to ground us.
Now I know, and this has always baffled me, and I tend to sort of avoid it when I write articles, which is that astronomers will reference, especially in their research papers, the distance to objects using
redshift.
A Z value, right?
Yes.
A redshift value. They say Z equals 5 or something like that.
We're bad.
What on earth does that mean? Right?
Well, when we started this conversation, we talked about how Vesto Slipher had measured the Doppler shifting, the red shifting of the galaxies, and the mathematical way of translating this is, if you take the wavelength of the light that you observe and you subtract off the wavelength of where you expected the light to be, and then divide all of that by where you expected the light to be, this gives you a fractional offset, basically. And that value mathematically is called Z. It's Z, pick a term.
Z, for you Americans out there, you could say Z, sure.
Redshift is probably the best way to confuse fewer people.
Yep.
And so this redshift value is just the fractional shifting of the wavelength of the light. It's what you can observe. To get beyond this fractional shifting of the light requires you to make assumptions about space and time. It requires you to make assumptions about how the universe is expanding. So when we work to translate that fractional observed shift in the color, we have to say, okay, so what value of H naught are we going to accept? What mathematical value for the density of mass in the universe are we going to accept, the omega value? And it's only once you make assumptions about those values that you can translate that redshift into a distance. Now, the easy way to think of it is anything greater than 1 is really far away. What's kind of amusing to me is when I started grad school, I observed the high redshift universe. I looked at things at a redshift of 1.2, 1.3, and a galaxy at a redshift of 1 has a look-back time of roughly 7.5 to 8 billion years,
wow,
depending on how you look at it. So you're looking back to more than half the age of our universe. Now,
right. I mean, compare that, like, as I mentioned, right? Andromeda at 2.5 million light years away. You're only looking back 2.5 million years ago. You know, other objects in our supercluster are in the 10 to 50 million years old. So you're seeing galaxies that are 6 billion, 8 billion light years away, and that's considered a low redshift.
Now, well, so a Z of 1 is now considered a moderate to low redshift. It all depends on who you're talking to.
Right.
Supernovae people, they're starting to push out further than that, but the majority of what we see is in that Z equals 1. But it's kind of crazy the way we can never get all the way back to the beginning. So the high redshift things that we look at, they're at a redshift of order of 4. Some of the highest things that we've looked at are estimated to have redshifts of 6. And this is where we start looking at light that came from more than 12 billion years ago.
Yeah, I mean, galaxies are being turned up now using like gravity lensing that are only 500 million years after the Big Bang.
And so greater than 4 means that you're looking at the first 1 to 2 billion years of our universe. And it's been amazing to me to see how just our definition of high redshift observing has changed from z greater than 1 is high redshift to z greater than 4 is high redshift and 1 is nearby. As our technology has increased, as we've pushed out further, it's like with race cars. The definition of a high-speed race car has changed since the 1920s. Well, now our definition of observing the high redshift universe has changed as well.
And there's some calculators out there. I know Wolfram Alpha will
Right.
usually convert that kind of thing, so you can put in, the
No, the
ratio,
best
and
the
you'll
best
get a
one out there is Ned Wright's. He's
Ned
at
Wright's? Okay.
UCLA. Just type in Cosmological Calculator. It will take you to his JavaScript page. It has perfectly reasonable default values. I know lots of scientists who I remember the first time I had to calculate this stuff, I sat there and I wanted to cry after they discovered what we're talking about in our next episode, which is the cosmological constant. And Ned Wright just programmed all of it, so no grad student ever needs to cry over doing this again.
Right. You do it once, and then you use his calculator.
Yes. You prove you can do it, and then you move on with life. It's like long division.
So as I mentioned, we're still reporting on stories. I mean, and we did one, must have been 6 months ago, about astronomers, narrow in, decide, calculate the most accurate measurement for the expansion of the universe ever, and then that number you just quoted. So how big are the error bars now? How much more do they have to go to really get to the bottom of this?
It depends on which way that you look. So some of them, they have 15% error, some of them have 5% error, but what's awesome is all of these overlapping error bars are in fact overlapping. So when you put all the pieces together, it looks like we're probably good to plus or minus 3 kilometers per second per megaparsec, which is kind of awesome.
That's pretty amazing. Hubble would really appreciate that precision.
Yes.
Since he was probably off by a factor of 10, but cool. All right, cool. And so as you mentioned, next up we're going to talk about the cosmological constant, which is Einstein's biggest blunder. Way to go, Einstein. All right.
Blunder and discovery.
Blunder and discovery. Well, thank you very much, Pamela.
Okay, I'll talk to you later.
To you next week. Bye.
Bye-bye. And it's not actually next week. It's now, but I'm going to save, and clearly you're going to save.
Yes. So hold on, everybody. We'll just let us save, and then we will take some questions.
And I have to admit, I had a tornado siren going off, so I'm also going to figure out why, because it's sunny, awesome day right now.
Weird.
Yeah, somehow it's not the first anything of the month, so it's just decidedly confusing.
Okay, I have saved and exported, so we are safe.
Okay.
Cool. So if anyone has any questions for us,
so
we'll be glad to. You're just clinging to that Mac. Time to move to the future. Get a Linux box.
It doesn't run Photoshop. That's going to be my answer until it runs
so
Photoshop.
Citizen Gold mentioned using Wolfram Alpha, which is so cool, that Andromeda is 0.788 megaparsecs. So I roughly calculated in my head to 1 megaparsec. I think it's better than Hubble did, right?
Yes.
Let's see.
I have no idea why we had a tornado siren. Okay, I'm going to move on with life.
So question from Harvey. So is it possible that the edge of our universe will be expanding faster than light? Love this question.
So
will the edge of our universe be expanding away faster than the speed of light?
We have to be so careful with our language on this topic.
All right, so rephrase the question
of the observable universe.
The edge of the observable universe.
Which has nothing to do with any actual edge, because there isn't an actual edge. But there is a volume of space that we are able to see, just like if you're in a fog that isn't completely opaque, there's a volume of space within the fog that you can see. And as you move through that fog, that volume moves with you. Well, if we were able to move through the universe, the volume of the observable universe would move with us. Now, when we look at that observable sphere, the edge of that observable sphere, we've now reached the point, we think, that that edge is actually falling off because it's starting to travel faster than the speed of light. But it's not actually traveling. It's the space between us and it is cumulatively expanding.
Enough with the non-answers here. Yeah, okay.
So it's cumulatively expanding to have an apparent motion greater than the speed of light, but nothing moves faster than the speed of light. Relativity has not been broken.
So yes, those galaxies are moving away from us faster than the speed of light.
No, they're not moving.
I know. Okay, the space, the space between us and those galaxies is increasing at a rate so that those galaxies appear to be moving away from us faster than the speed of light. In that, light generated from those galaxies will never reach us.
And this is sad because before we realized just how the expansion was going, there was this idea that every moment you see a little bit more of our universe because more time has transpired and more light has had time to get to us. And no.
Just the opposite. Every moment we see a little less of our universe because
it's
more of it is dropping off that horizon.
Yeah.
There was a great there's a great study that was done again a couple of months ago that they essentially went back and calculated like what would be the best time to be an astronomer, and it was about 1 billion years after the Big Bang. That astronomy has gotten worse since that point.
How did they define that?
Just, lots of things to see. Things were relatively close, so you could observe them. Lots of active star formation, lots of interesting things happening all at that same time. So, yeah.
The universe at the same time was too small to be able to notice things like the cosmological constant necessarily, and large-scale structure hadn't had a chance to really get itself that much started. So it depends on what you're interested in. There's different times for different ideas.
Iwan Timmermans asks, so if we're looking in the past and Andromeda is getting closer to us, could it be that it's closer to us than we can actually see?
I don't understand the question.
So we're seeing Andromeda.
Mm-hmm.
It's moving towards us.
Mm-hmm.
We're seeing it 2.5 million years in the past.
Yep.
So is it closer than we see it?
Yes. Yeah.
Yes. It's
yes.
2.5 million
that whole light travel time
years.
It really mucks things up. Yeah, it's closer than it appears.
It's 2.5 million years worth of movement closer than we see. But, like when's Andromeda collide with us? In like 5 billion years? Yeah. So it's a lot. But I guess the point being that as it gets closer, then our future descendants will see it in more and more closer and closer to real time until they're seeing Andromeda
and this
immediately.
Is why you see the light getting blue shifted, because as Andromeda is creeping up on us at a not very slow velocity, the light gets squished by its motion in a way, because the beating of the crests of the wavelengths get compressed, because as the beating regularly comes off of the stars, the star is getting closer and it's compacting those waves. I don't know if that makes sense.
So another question completely unrelated to our discussion today. Side note, given that these podcasts may be released after December 7th, do you have any embargoed info on the Mars Curiosity discovery that everyone is buzzing about? Now, the problem is that this is live, and so even if we did have embargoed information, we wouldn't be allowed to talk about it. But I can tell you that I don't have any embargoed information on it.
I don't have any embargoed information.
We are in as much the dark as anybody. However, today at 4 p.m. Pacific, we're going to be doing another show with Emily Lakdawalla from the Planetary Society, who is one of the most about the Curiosity rover and is one of the most knowledgeable people in our business about this. And I will grill her, and we will brainstorm, and we will try to sort of figure out what kinds of possible discoveries could be coming down, because she knows the
capacity of the instrumentation.
She knows the instruments, she knows the things they're looking for, and has talked to enough planetary scientists to know what kinds of things they would consider to be earth-shaking as opposed to lame. But
the problem is we have such a low bar for earth-shaking when it comes to Mars.
Yeah.
Earth-shaking could be that they found that there'd been water more recently on the surface of Mars than we thought due to various yada, yada, yada geology.
I think a lot of people are going to be disappointed if that's what they say.
Right, but it could also be, oh my God, they found organics in amounts unexpected. And I'm thinking that the reality is going to be somewhere between those two.
Yeah, or methane, a discovery of methane either
methane.
Into I mean, they thought they found methane in the atmosphere, and then it turned out that it was methane that they carried from Earth. So if they actually do find methane, that would be really interesting because it takes, methane needs to be produced by some source. The thing is that when they said, they said Earth shaking, I was actually thinking something like tectonics, because one of the big unknowns about Mars is, does it have volcanic activity in recent history? Is there any kind of tectonics happening? And so if they discover...
we know that the result came from Sam?
Well, that's the thing, right? But I was just thinking because they called it Earth shaking, that was...
I think that was just like poetic license.
One for the history books. So it had better be... I think heads are going to roll. I think
eyes are gonna roll.
I think actually, I gotta say, I'm amazed that he made that announcement on NPR. Like, NASA does not do things that way.
I'm suspecting sleep deprivation had something to do with it. The Mars guys are really their bodies get off kilter. That extra 45 minutes.
I would not be surprised if someone's getting yelled at right now for letting that slip, because now it's out of control, and NASA's trying to sort of set an announcement time, but they have to confirm and double confirm, and it's going to take a little while.
And they don't want to repeat the Mono Lake announcement of doom.
Yes, about the discovery of arsenic-based life,
which was not.
Yeah. So anyway, this is a preview of the conversation that I'm going to have with Emily in about 3 hours.
Yeah.
And we will hash and rehash and speculate, and you will see, something akin to the worst political speculation, leading up to an election, except us trying to figure out what.
It will be scientific speculation based on the capacities of the instrument.
Meaningless nonsense speculation from us. Yeah, it'll be fun. So anyway, we're going to do that at 4. So you can dig through, do a search for Curiosity on Google Plus, and you'll see that event, and we'll be doing that. It'll be fun. Someone's mentioning on YouTube it was the lead investigator of the who made that announcement on NPR. So again, in all of my experience with NASA, they never do things that way. Anytime I interview folks at NASA, there are PR people in the room overseeing every comment that gets made. They run a very, very tight ship there. So,
but at the same time, one of the things that consistently impresses me is there aren't that many people who are at the highest levels of the missions. So you have this very small cadre of humans that are the instrument leads or the mission PIs are basically handling planetary space exploration. And this small cadre of people, they're writing grants, they're managing huge staffs, they're traveling between NASA centers, visiting colleagues in the European Space Agency, they're traveling the world, presenting their research, collaborating, herding cats.
Yeah.
And I know how tired I get keeping up with them, and I'm just mission support and a communicator of science. And so sleep deprivation happens, and we all say things we shouldn't when tired. Drunk, same thing. One's more fun than the other.
And I think people don't necessarily, they've been talking about something for a while, and they don't necessarily need to put it in context. They don't know whether this is like because, sometimes when scientists say something's really amazing, it's actually not that amazing to the regular people. It's really amazing to scientists, but, not that big of a deal to anyone else. So, anyway, a couple of
eye rolling,
questions
head
here.
rolling, something will happen in the next few weeks.
It's going to... now the speculation is on now that grinding is going to happen. This is going to come out in bits and pieces. I mean, we've seen this happen a lot. I mean, now this is, this is my world now. This is how this works. We crack it out of them bit by bit. So, and Emily is one of the best people to do that.
Yeah.
I mean,
And she digs into the data. She approaches it as a scientific scavenger
planetary
hunt.
geologist. Yeah, absolutely. Okay, well, why don't we wrap this up then, because we got to get on to that next show. So we're going to be doing the next show in just a
like
few
10
minutes. Yeah, we'll just give us a
just
chance to have a coffee and and go to the bathroom and such, and then we will sort of start up the next episode. So there should be another event there that you can go and so you can leave this one and go to that other one, the one that's 280, the Cosmological Constant, and we will start that up in just a few minutes. So thank you very much, Pamela, and we'll see everybody. If you want more Astronomy Cast, we'll be doing this again. Okay.
Sounds great. Talk to you later,
Bye.
Fraser. Bye-bye.